So today we'll talk about parallel algorithms. Slightly different topic. What's the story about? All the modern computers are parallel computers. So even if your laptop, there are not single processor, but there are multi-core processors. So your processor contains multiple cores and they make calculations simultaneously. And that's basically because we kind of reach the limit of the speed of the processor. So when I was young, the speed of the processor meters by the number of how it's called, I'm not sure, number of steps that your processor made in each second. So there was like 100 megahertz computers, then like 200 megahertz processors, then gigabyte processors, and now we had something like 3 gigabit processors. And why don't we have more than 3 gigabit processors? Basically because we reached the limit of the like physical limits on the speed of the processors. Let's say let's talk about physics a little bit. So in physics you have a certain limit of the speed. So you have a like speed of light. So you cannot pass the signal from here to here faster than speed of light. And if you have like 3 gigabit processor, 3 gigahertz, then it means each second you make 3 billion operations. And speed of light is like 3 by 10 power 8 meters seconds, something like that. So if you just measure the distance the light travels when you make one operation in your processor, the distance is about, so you need to divide like this by 3 billions. So if you divide this by 3 billions, you have something like 1.1 meter. It means that when your processor make one operation, that light's traveling like 10 centimeters, and the size of your processor is like few centimeters. So you basically cannot make it much faster than it is now. So all the modern processors basically reach the limit of the speed of the processor. You not exactly, but quite close. So what are they doing? They, instead of increasing the number of operations per second, they increase the number of different cores in your processor. So all the modern processors have like 4 cores, 8 cores, and so on. And you have your, how it's called, GPU. In GPU there is much more small processors. So basically what we're doing is we increase the speed of calculations not by increasing the number of operations per second, but increasing the number of cores which simultaneously, which like solve your problem in parallel. So it's very interesting to learn how to make your algorithm work on parallel processors. That's what we're talking about. So what is a parallel RAM? First let's talk about parallel RAM model. So you have PRAM model. So what is it? So RAM is just random access memory, and P means parallel. So what we have? We have our RAM, and we have some number of processors. So we have some RAM, and we have some number of processors, and they access this memory at the same time. Let's say we have P processors. So what your algorithm look like? Your algorithm looks like all your processors make some operations simultaneously. So you have like first processor, second, and so on. P processor. Each processor has some operations. And we kind of want to optimize the time when all the processors finish in doing the operations. So we find the maximum number of operations here and calculate this time, let's say TP, like this. So TP is just the time that P processors need to solve the problem. Now what about memory? It's slightly more complicated than before. So when you have multiple processors who access the same memory, what happens if several different processors try to access the same element of your memory? Well, it depends. So again, it's some parameter of your model. In some models, we only allow each element of your memory be accessed by only one processor. So we don't allow to read the same cell of the memory by two processors at the same time, and we don't allow the cell of your memory be written by two processors. So it's called exclusive write, exclusive read, exclusive write. So exclusive means only one processor can read the same element of the memory. That's sometimes it's enough. For some algorithms, it's enough actually to allow only one processor to read the same element each time. Again, each cell can be read or written only by one processor at each moment of time. So you can read this element here, and then in the next step you can read it here. But you don't allow to do it simultaneously, right? In some other models, we actually allow the same cell to be, for example, read by several processors. So if we allow two processors to read the same element of the memory at the same time, it's called concurrent read and exclusive write. Actually, reading the memory is not a big problem. Yeah. So if you have some element of your memory, you can read it by two processors. They just have the same result. It's not a big problem. Yeah. Much more interesting what happens when you try to write the same element of memory at the same time by several different processors. It's called concurrent read and concurrent write. What happens when you try to write the same element of the memory at the same time by two different processors? What will happen to this element of the memory? It depends. So again, it's some parameter of your model. In some models, let's say when you try to write the same element at the same time, then, for example, any of the processors can write. So the final result in this cell will be just a random one of the elements you want to write. So if one processor tries, if you have some element here, and one processor tries to run here one, and another element tries to write here two, then the final result in this cell will be either 1 or 2 at random. In some other models, we actually write let's say all the processors have some IDs. So the only processor with the smallest ID writes this data to this element. So again, it's like slight difference between the different models. In our case, it will be, I believe in the algorithms we discussed today, it's not a big difference, but for some algorithms, it may make big difference. So, actually, it can be proven that if you can write algorithm in this model, you can write in this model, just the time complexity will be multiplied by some logarithms. So the difference between these models is at most logarithm, but still the logarithm is like important. So if you have linear algorithm or n log n algorithm, it's kind of it's different, right? We don't want to have extra logarithm in our case. Okay, that's all. So that's how the parallel algorithm works. So you have several processors. Each processor makes some instructions, and the total time is the time when all processors finishing doing their instructions. Okay, this model is fine, but it's actually pretty hard to implement. For example, not hard to implement, but it's hard to implement the algorithm in this model. So you kind of want to, if you have some algorithm, you want to manually assign the different operations to different processors and to keep track what processor is doing what stuff. It's kind of complicated. So instead, sometimes we use different model, slightly different actually. Let's introduce like this. Imagine you have a graph of all operations you need to perform. So you have some graph like this, and they have some dependencies. and so on. So here, and something here, and something here, why not? So you have some number of operations. Again, each node of this graph is one single operation. Basically, you can do it in constant time, right? And these arrows express some dependencies between these operations. So you cannot make these operations until you make these two operations. It's actually quite intuitive, right? So if we look at the graph of all operations and dependencies between them, let's think about how much time we actually need to implement to execute all these operations if we have some number of processors. For example, if we have only one processor, let's say T1. If we have only one processor, then how many operations do we need? Let's say something. Again, you have a graph of all operations you need to perform and some dependencies between them. If you have only a single processor, how to calculate the total time you need to implement to execute all these operations? No, 7. Okay, so for this graph is 7. But in general, if you have some graph, it's just the number of nodes in this graph. Okay, I'm just checking your listening. Okay, so it's just number of nodes. This number of nodes. Number of nodes. Okay, this parameter, the number of operations you need to perform, is called work. So number of operations we need to perform is just called W for work. So it's total work we need to do. Now, if we have infinite number of processors, and how much time do we need to execute all these operations? What do you think? How to go again? That's actually a nice graph problem. You have a graph, you have some dependencies, and you have infinite number of processors. Then how much time do you need to execute all these operations? Any ideas? One is not enough, so you cannot make all the operations at once because you have these dependencies. So to execute this operation, you need to execute this operation before. And to execute this operation, you need to execute this operation before. So you cannot execute all the operations at once. Yes, actually the time you need is the maximal distance in this graph. So in this graph, we have this critical path, like this. So this path contains 4 nodes. So we need at least 4 operations to execute all this. Yeah? So minimal possible time is 4. Now let's try to find all such paths and calculate the longest path. So the longest path corresponds to the minimal number of operations you need to make to execute all this. Max path. It's called depth. That's all. And now we have these 2 parameters. We have this W and this D, work and depth. It's actually it's called work-depth model. Now I claim that these 2 values is actually enough to calculate the time complexity for any number of processors. Now imagine you have some P processors. Imagine you have P processors and you have some automatic scheduler. So you have some special algorithm which assigns these operations to some processors. So when you have some free processor and you have some operation you can perform, you just give this operation to this processor and so on. So you have this as just automatic scheduler. Let's say we have this. It's quite interesting topic, how to implement good scheduler, but not today. So imagine we have automatic scheduler which assigns these operations to some processors in optimal way. So if we have P processors, I forgot how to write. What will be equal to TP? Let's think about how many operations we actually need to implement or to execute all this. How much time do we need to execute all these operations? No, first of all, let's make two obvious lower bound. First of all, this must be at least S, right? At least D, right? So if you have P processors, you can't make it faster than in D operations, right? Second limit is that TP must be at least W divided by P, right? So W is total number of operations. If we have P processors, we cannot make it faster than W divided by P, right? So I claim that TP is at least maximum of D and W. And maximum is actually the same as the sum. So this maximum is at is at least 1/2 of D plus W over P. So the number of operations we need is actually big omega of D plus W divided by P. And now the interesting fact. The interesting fact is actually we can implement this algorithm in this number of operations. So interesting fact is TP is actually big O of D plus of P. So this lower bound is actually reachable in, like, the same asymptotic is actually reachable. Why is it true? Why is it true? Well, let's see. Let's say we have P processors, and we want to implement this algorithm as fast as possible. So let's split all the tasks in some layers. So let's say the layer of the node is the distance from S, from the starting node. We have the starting node. So let's say that the layer of the node is the distance from S to this node. Like, not the distance, like length of the longest path from S to this node. So here we have distance 1, here we have distance 2, here we have distance 2, here we have distance 3. Now we split all the operations into some layers. 1 layer, 2 layers. Now, how many layers will we get? So if we split all the elements by distance from S, we will have D layers. Yeah. So here we have D layers of operations. We can execute the operations layer by layer. So we first execute all operations in the first layer, then all operations in the second layer, then all operations in the third layer, and so on. So let's try to execute all operations layer by layer. Now, let's say we have n I operations in layer I. Then, how much time do we need to execute all operations in layer I? What do you think? So we have P processors. And in layer I, we have NI operations. How much time do we need to execute all these operations? NI over P. That's more precise. So, number of operations is actually NI over P but it should be rounded up like this. So it's cell of an A. Now we need to calculate this sum. So this is the total number of operations we need. Now, this thing is no more than Ni over P plus 1, right? And now we calculate this sum. We sum all these things. It will be just W over P. And sum all these things. So we have D elements in this sum. So in each element of sum we have this 1. So if we sum 1 D times, we have D. So if we just execute all operations layer by layer, total time we need is just W over P plus D. And the minimal time we need is half of this. So we have like asymptotically optimal way to assign the operations. That's all. What's this all about? What's it all about? What's the interesting thing? Interesting thing is actually that you only need to analyze these two values. If you optimize these two values, then you will optimize the time complexity of your algorithm for any number of processors. So if you just find these two values, then you basically need you know the time complexity of your algorithm for any number of processors. That's all. Let's write it like here. Now, what happens in practice? In practice, what happens? You have some number of processors. This number is actually usually pretty small compared to the size of the input. So, well, let's say you have two different algorithms. So you want to optimize two parameters of your algorithm. That's a little bit complicated. Let's say we have two different algorithms. One algorithm has work of n and let's say depth of log square n. And another algorithm has work of n log n and depth of log n. Something like that. Okay. So Ni is number of operations in the layer. So if I just sum all these things, yeah. So sum of all. So Ni is the number of operations in the layer, and W is total number of operations. So sum of all Ni equals to W. P is a constant, so I can move this constant away. So I have sum of all Ni's. It is W divided by P. So let's say we have two algorithms. One algorithm has total number of operations n and depth log square. And another algorithm has number of operations n log n and depth log n. Which algorithm is actually better? What do you think? It's actually not an equation. Not an equation. In some situations, both of these algorithms can be optimal. Yeah. So for some inputs, you may have this algorithm optimal. For some another inputs, you may have this algorithm optimal. So it depends on number of processors and on size of your input. So it's not that easy. But usually what happens? Usually this P is much smaller than the size of your input. So usually you happens like, if you want to make a parallel algorithm, it's usually when you have very large input, right? If you have small input, you can solve it in one processor fast enough. So usually the size of the input is pretty large. So comparing to this number of processors you have. So usually in practice, this first sum is much more interesting than the second thing. So usually you want to optimize this part first and then optimize this part. So what we will try to do in this lecture, we will try to make algorithm which has the optimal work time and some good depth. So if we have this, so what we'll ideally what we want to achieve, we want the work be the same as for the one processor algorithm, and this depth to be something like log n or log square, or okay, even square root of n is usually good enough. So I want this work to be the same as for the single processor, and I want this depth to be as small as possible. Usually log is enough, log square is enough. Again, square root of n is slightly worse, but still pretty good, and so on. Again, usually this part is much smaller than this part, so I kind of want to optimize first. First, I want to optimize this work, and then I want to optimize that. Not always, but usually this is what happens. Let's go. Well, let's start from something simple. Let's have an array and try to calculate the sum of this array. So let's say I have array A, and I want to find the sum of all the elements in this array. So what is my goal? My goal is to make algorithms which have the same time complexity as the single processor algorithm. So I want my work be the same as the time complexity of the single processor algorithm. The single processor algorithm will basically be linear, right? So you can calculate the sum in linear time. So I want the algorithm with linear time complexity, linear work, and small depth. So how can you parallelize the calculation of the sum in the array? Any ideas? What can you do if you want to calculate the sum of many elements? Break into parts. That's a good start. So we can break the array into some. But what happens next? You break the algorithm. You break your array into parts. Let's say you have n processors. So you break your array into parts. Each part contains a single element. What to do next? How to? Yes. If you have small number of processors, you can break your array into parts, and each processor calculate the sum in each part. But then you need to combine all these sums into some big sum. Yeah. But again, that's a good start. So you have the array. You want to break it into parts. Now each processor calculates the sum in his part. But what next? You have many. You have the same problem. You have many elements here, and you kind of want to calculate this sum. Actually, you can do it. You can do the same thing again. You can you have these sums. You can break them into parts of by t. But yeah. We'll do it in easy way. So what we can do? We can build this actually a segment tree for the sum. So we have these elements. Let's calculate the elements. Let's put some elements. Let's say 3, 5, 2, 6, 2, 1. 3, 4. So we have this array. What we can do is first to calculate, basically we need to build a segment tree. So first we calculate sums of all pairs. Here 8, here is it 8, here is it 3, 7. Then calculate sum of pairs like this. So we have 18, we have 10, and then calculate this one. Now, how can we do it in parallel? First, we can calculate all elements here in parallel. Yeah. Then we calculate all elements here. Then we calculate elements here. So all the operations in the same layer are independent. So we can calculate them in parallel. So we calculate all elements here, then all elements here, then all elements here. Total number of these steps is log n. What is the total number of operations? Total number of operations is number of nodes in your segment tree. Number of segment tree is equal to n. Yeah. So you have 2n operations. No, actually n. Yeah, if we ignore this first. So we have linear number of operations and log n steps. So we have algorithm with work linear and depth log n. That's actually pretty cool. That's what we wanted, right? So we have the algorithm with the same number of operations as the single processor algorithm, but with very good parallelization. So log n is actually usually the best you can get. If you in some purpose. Okay. So usually you want something like that. So you want the algorithm with the same time complexity as the single processor algorithm, but they're like log n or log square n. Yeah. Nice. Okay. That's this one of the most important algorithm actually in this case. So we usually will make something like that when we try to calculate. Go. So next. Okay, let's introduce some important operations. Why is linear? Because number of nodes in the segment tree is linear. So we have n plus n over 2 plus n over 4 and so on. So if you calculate sum of this, you will have 2n. Yeah? So number of nodes in the segment tree is 2n. That's why it's linear. Go. So first important operation is a map. Map is an operation which just takes the array and applies some function to all elements of the array. So we have like array AI and we want to make array BI equals to f of AI, something like that. Well, it's actually a pretty simple operation. You can do, since you can calculate all these values in parallel, then actually it's maximally parallelistic. So you can just calculate all these functions in the same time. So here the work will be linear and the depth will be just 1. No, if you can, it actually depends again. Sometimes, so if you can make n processors at the same time, then you can do it in one operations. Actually, in practice, you cannot make, you can create n processor in constant time. Yeah, so you usually slightly more complicated. Usually you allow only to fork in two processes. So if you can fork only in two, if you can in each fork you can make only 2 branches, then you actually need to log n forks to make it work. But next operation is reduce. Actually, what we want to do is to calculate some function. So we have some, let's say, plus some associative function. Associative function. And we want to calculate like a1 plus a2 plus and so on plus an. No, and the way you do it is the same as here. Yeah? So you just do the same thing, but instead of sum, you take this associative function and calculate the value for the whole. It's actually quite cool. So you can calculate sum, you can calculate minimum, I don't know, any other associative function you can imagine. So you can calculate any associative function for the array in the linear work and log n depth. So again, the work will be n and depth will be log n. Now let's do something more interesting. Next operation is called scan for, I don't know why, for some historical reasons. What I want to do? I want to calculate the prefix sums in my array. So I have array A, and I want to calculate array B such that BI is sum of all elements aj, let's say j from 1 to n. It's basically prefix sums, right? So for each prefix, I want to calculate the sum of elements in this prefix. Well, how you do it when you have a single processor? When you have a single processor, okay, let's do it for this array. So how you do it for single processor? You have this array. You go from left to right and calculate prefix sums. So first you calculate the first prefix sum is 3. Then you calculate the next one just by adding the next element. So you get 3 plus 5 is 8. Then 8 plus 2 is 10. Then 10 plus 6 is 16, and so on. Each time you take the previous prefix sum and then your element, calculate your sum, and you have the next prefix sum. Like this. Okay, it's now we need to do the same thing, but in parallel. So here I obviously move from left to right. Each new element depends on the previous element. If I just want to make it parallel, the depth will be n, right? So I just go from left to right. Each new element depends on the previous element. So again, I want to do it slightly different to make it more parallel. And the way I do it is again by building the segment tree. So again, let's build a segment tree for the sum for this array. Again, okay, I will do it again. Store sum and prefix, something like that, yeah. So now we have this segment tree. Now let's try to go again. We build this segment tree in linear time and log n depth. So let's go from root to the leaves and try to build the prefix sums. So we start from here. So the sum in the left part is 16. So I want to add this 16 to all elements in the right subtree. Yeah. So again, it's like divide and conquer, right? So I take the root, look at the left part, see 16. I want to add this 16 to all elements here. So let's just put it here. So I think plus 16. Now I go here. So I see this 8. So I want to add this 8 to all elements in the right subtree. Do it. So take this 8 and add it to all elements here. Plus 8. Now here, I want to add 16 to all elements. But I also need to add this 3 to all elements in this subtree. So I go to the left subtree and add this 16 to this subtree. And I go to the right subtree and add this 16 plus 3. So here I add 19. And so on. So each time you have some node. Yeah. So you want to recursively go to here and here. When you go to the left subtree, you just apply the same operation. When you go to the right subtree, you apply this operation plus the sum in the left subtree. So I go here, I add 16. I go here and add 16 plus 2. So from here, I go here and add 19. I go here and I add 19 plus 3. So it's plus 22. And that's all. And the same here. Go here plus 8, here plus 10, here plus something, so plus, let's say plus 0. So I go here plus 0, I go here 0 plus 3, it's plus 3. And finally you calculate this value, so it's 22 plus 4 is 26, here is set to 22, 19, 18, 16, 10, 8, 3. That's all. And that's your final array. And again, you do all operations in each layer at the same time. So all operations in each layer are independent. So you can do all these operations, then all these operations. Or total number of operations, again, is linear. And the number of these steps is log n. That's all. So that's how you can make this operation. It's actually one of the most important operations in this theory. Well, and finally, let's make one operation. Let's make filter operation. So again, we have some array A, and we want to build array B, which contains all the elements from array A such that f of A equals to 1. Again, for example, let's have some array again. Let's have 3, 5, 2, 6, 1, 7, 3, 2, 1. And let's say, too many. Not good enough. So let's say I want to filter all even elements from this array. So f of x is x 2 equals to 0. So what I want to find all the even elements in my array. This element, and this element. So this is my array. And I want to build array B like 2, 6, and 2. That's all. Nice? Yep. So first of all, how to find the size of array B? So how to find the number of elements such that this function returns true? Simple question. So first of all, I want to find the length of array B. So length of array B is the number of elements such that this function returns true. How to find the number of these elements? Apply the function and then calculate the sum. Yes. So you first apply the function. You can do it in parallel. So it's independent for all. Basically, you make this map operation. Okay? So you apply the function. Let's use some other color. Green. So it's 0, 0, 1, 1, 0, 0, 0, 1, 0. Then you calculate sum of all these booleans. You have 3, so 3 is the size of your array. Nice, nice. Now, we know that in the final array there are 3 elements. So let's, how it's called? So let's initialize the array of 3 elements. So now we have this array of 3 elements empty. Now, what I want to do, I want to put this element in the first position, this element in the second position, and this element in the first position. How can we find the position of the element in the array B? So I have these 3 interesting elements. How to find the position of this element in array B? Prefix sums. True. So you make this array of booleans and then calculate prefix sums. The prefix sums will be, again, so this 0, 0, 1, 2, 2, 2, 2, 3, 3. So these will be positions of your elements in there. And now you just again, you can do it in parallel. You can take the element. If the function is true, you put this element in this position of array B. So you take this element and put it in the first position, take this element, put it in the second position, take this element, put it in the first position. And again, you can do it in parallel. All these operations are independent. That's all. That's all. So again, how to filter elements? First you apply your function. Then you calculate prefix sums. Calculate the total number of elements in array B. Then you initialize the array. For each element, you know its position in array B. So you just take the element and put in the corresponding position of array B. This all can be done in parallel. So the total work will be, again, let me write it here. Total work will be n, and total depth will be again log n. Okay. Now let's do something more interesting. Let's make a sorting algorithm. Let's make a parallel sorting algorithm. Now, do you remember how merge sort algorithm works? Yeah. So I want to take the merge sort algorithm and make it parallel. That's my plan. So merge sort. So how the merge sort algorithm works? The core operation of the merge sort algorithm is just to merge two sorted arrays. So I have this one array, second array. Let's look at this. Oh, let's look at this. So I have array A sorted, and I have array B sorted. I want to combine all these elements into some array C. Like this. Where is the plate? Not yet. I didn't apply parallelism. I just say how the merge sort algorithm works. The merge sort algorithm works like this. You have this core operation is to merge two arrays. When we learn how to merge two arrays, then we will apply all the same technique from the merge sort algorithm. No, in merge sort algorithm, you call recursively for the left part and the right part. You can do it in parallel, obviously. And then you take the sorted array from the left part and sorted array from the right part, and you need to merge this array. And this is interesting. Yeah. So again, what happens in merge sort? You have the whole array, you split it into two parts, then you recursively call for both these parts. This can be done independently. So you can make parallel sort for the left part and the right part. And now finally, you need to merge these two sorted arrays into single sorted array. So this is how the merge sort algorithm works. You split your array into two parts, call recursively for left and right part, and then when you return from the recursion, you need to merge these two arrays into a single array. We may break into P. Yeah, that's good, of course. Let's not think about P. Okay, let's talk about the depth amount. Imagine you have an infinite number of processors. So if you think about P, if you think about like constant number of processors, it's a little bit, yeah. So usually it's easier to think about how can I implement this algorithm if I have infinite number of processors. What is my time complexity? Again, you can split your you can split both arrays into some parts, but what next? What will happen next? Okay. Why this idea doesn't work? So if I split first arrays in part and second array in parts, and then merge these two arrays, these two arrays, these two arrays, and these two arrays, and then just concatenate them, will it work or not? What do you think? And sort each level and yeah, no, yes, yes, you can do it. Yes, if you make merge in linear time, then again you have n log n depth. N log n depth is kind of not interesting. No, n depth. Okay, okay, the work will be n log n and depth will be n. It's interesting, but not much. So I wanted depth to be less than n. Depth n is a little bit it's not that interesting. Elements of A must be small, elements B. Yes, exactly. So what can happen that here you have all small elements, and here you have some big elements. So if you just combine these two parts, you will not have the prefix of your array. So what I want to do, if I want to take these two arrays and put them here, it will not work. Because here I might have elements like 1, 2, 3, 4, 5. And here elements like 10, 11, 12, 13, and so on. So if I just merge these two parts, then here I have element 4. Element 4 must go before all elements here. So it's not working like this. But it's pretty close to the actual algorithm. Let's do it like this. Okay. Idea number 1. Let's try to find the position of each element in the final array C. So again, no, yeah, okay, okay, let's put some arrays here. Let's put some arrays to 1, 2, 4, 7, 10, 17, 25. And something here like 3, 5, 6, 11, 12, 20, 21, something like that. Let's try to find the position of each element in array C. So I have this array C. I know its length. Again, let's try to put each element into corresponding position in array C. So how to find the position of element in array C? So let's take some elements. So let's take this element. Okay, let's take this. Not interesting. Let's take this element. Let's take this element 10. Yeah. How to find the position of element 10 in the final array C? To find the position of element in array C, I need to find the number of elements which must go before my element. So which elements must go before my element 10? Well, these are all elements in array A, all these elements. So all these elements must go before my element 10. And some elements in the second array. These are all elements which are less than 10. These are these ones. So these elements must go before my element 10. So my position of my element will be 1, 2, 3, 4, 5, 6, 7, 8. So position of my element is 8. Right? Yeah. Now, to find this number, we need to make a binary search. Right? So we can do it by making binary search for each element. Again, for each element, we make a binary search in another array. When we make this binary search, we can calculate the position of this element in the final array. Now, in the end, we take each element and put it in this corresponding position. Now, all these binary searches can be done in the same time. If we allow concurrent read, yes, if we allow concurrent read, we can do these binary searches at the same time. So we do this parallel binary search for each element, find the position, find this position, and put this element in the corresponding position. What will be time complexity? Okay, what will be the work and what will be the depth? What do you think? Of this single merge operation, not of the whole merge sort, but of this single merge operation. If I have n elements here, what will be the total time complexity of this? Well, let's talk about work. Work is just total number of operations. For each number of operations, for each element, we need to make binary search. Binary search takes log n operations, so the total number of operations is n log n. And the depth will be log n, because for each element we make binary search, but we make all these binary searches in parallel, so total number of steps we need to take is log n. Now, if we do it like this and then apply our merge sort algorithm, the total complexity of the merge sort algorithm will be, again, it will be merge sort, will be n log square, and depth will be log square. Yep. Again, in the merge sort, we just apply the same thing in each layer. So in each layer, we have this time complexity, so we just combine this for log n layers, we have this complexity. Now, what's here? What's here? Okay, this log square is not a problem actually, but this log square is a problem. So we know that we can sort elements in log n time, in n log n time, but here we sort elements in n log square time. That's kind of, that's not good. Yeah. So our sorting is actually slower than the single processor sorting. We can improve this. We can improve it. How can we get rid of this log square? To get rid of this log square, we will get rid of this log n. So our plan is to eliminate this log n factor from here. How to eliminate log n factor? No, we did multiple times. To eliminate some log n factor, you just split all elements in groups by log n, and then do the same operation for these groups. So what we'll do, I'll take both my arrays and split them into groups of log n. Now let's say log n is 3. Okay? Let's see. Okay. Two pointers, you can't make 2 pointers in parallel. I want to make it for each element independently, so not working. So 2 pointers algorithm is basically a sequential algorithm. You cannot do it in parallel. That's actually sad, but good thinking. So what? Let's split the first array into groups of size log n. First group, second group, third group. Now, for each group, let's find the position in the next array which splits in the same way. So I want this split between these two groups and find this split between 4 and 7 in this array. So I will, basically I will find all elements less than 7 in the second array. So I will try to fix this one. So I find these elements are less than 7. Now I will find all elements less than 25. So these elements are less than 25. Any idea what I'm doing? Yeah? No? So, what I want to do, I want to align these two arrays kind of. So I want to align these two arrays, then these two arrays, and then these two nothing. So I have these two arrays, then these two arrays, and then this third. Now, what I will do next, I will merge these two arrays, then merge these two arrays, and then merge these two arrays, and then just concatenate the results. The plan is. But the problem is right now, I want all the small arrays have size at most log n. Now, all arrays in array, all these subarrays in array A has length log n, but subarrays in array B has length more than log n. And I want all these small arrays to be at most log n. So what I will do next, I will do the same trick for array B. So I will take array B, split it into parts of log n. Again, with this, take this, take this. And again, for each array, I will align it to some subarray of array A. So again, this is the same thing. So 20. So I need all elements less than 20. It's here. It's boring array. Oh my god, it's so boring. Let's do something interesting. These arrays are too boring. Let's do something. Let's do something. 1, 2, 3, then 10, then 12, 17, 27, 35. And here's something like 5, 6, 11, 13, 14, 28, and then something like 45, 60, something like that. Okay, one more time. So again, I split the top element in groups of log n. Now for each group, I find the position in the second array. So it's here. And this position is before 27, it's here. So I need to merge this array to nothing, this array to this array, and this array to this array. And now I will do the same for the bottom, for the second array. So for the second array, I will split it here, here, and top. So for this position, I find the corresponding position here first. So it's before 13, it's here. For this position, it will be before 45, it's here. So again, I split my second array in groups of log n, and I split my top array in groups of log n. Doesn't make any sense. Again, what I just did, I take some positions in the top array and find the corresponding positions in the bottom array using binary search. Then I took these positions in the second array and find the corresponding positions in the first array using binary search. That's all. Now. Yeah. Now, I split both my arrays into groups, and the size of each group is at most log n. So, now, what I need to do? I need to align this first group to this first group. Then this second group to this second group. Then this third group to this third group. This fourth group to this fourth group. And this fifth group to this nothing. I don't want to stop. Now, to calculate the final array, I need to merge these two parts, then these two parts, then these two parts, then these two parts. And I can do it in parallel. So in my final array, first three elements will be a result of this merge, so this one. Then I have 4 elements here, merge of these two. Then I need to merge these 2 elements, I have another 4. Then I merge these 3 elements, have 4, and then final here 5. So I can calculate size of each of these groups just by looking at these 2 arrays. Again, you just calculate the prefix sum, something like that. Now, I will just calculate each of these groups in a single processor, because the size of each group is at most log n. So I can calculate, I can merge this arrays and this arrays in a single processor in log n time. Just because size of this group is log n. So that's all. So I split both arrays into groups in parallel and then assign each pair of groups to a single processor. Because the size of the group is log n, the total time the processor needs will be at most log n. So the first processor took these two groups and put 1, 2, 3 here. The second processor takes these two groups and put like 5, 6, 10, 11 here. The third processor takes these two groups and so on. So each of these parts is calculated by a single processor. Now, total work is actually all these binary searches. Each binary search takes log n time, but we have n divided by log n positions. We need to make binary search. So we make n over log n binary searches. Each binary search took n log n time, is log n time. So the final work will be just n. And the depth will be log n, because this binary search takes n log n time. It takes log n time. And then these merges, each of them take log n time, and we do them all in parallel. So the depth will be just log n plus log n. That's all. That's how you make merge in linear work and log n depth. And if we use this modified algorithm for merging, then the total merge, then the merge sort will work like this. Nice. That's all. That's a merge sort. Can we eliminate this log square? So can we make a sorting algorithm which takes n log n work time and log n depth? The answer is yes, we can, but it's very complicated. So there is no simple algorithm which has log n depth to sort the arrays, but it's possible. It's even possible in the comparators network. So if we discuss some comparators networks in so it's called sorting networks. I believe we discussed sorting networks in the first semester. So sorting network is basically a parallel sorting algorithm. So it's possible to build sorting network with depth of log n and log n and log n comparators. It's possible, but it's really complicated. Not very usable. If we use divide and conquer array, oh, you can do it, but why do you need to? Sorry. Let's think. Okay, if we do it again. No, we already spent log n spent time. Just by doing these first binary searches, we already spent n work and log n depth. We can do recursively the same thing. We can do for each small subarray, we can do the same thing. We can split it again, make binary searches and so on. But it will not affect time complexity. So time complexity, even after the first binary searches, will be like this. So if you try, there's nothing to improve actually. Yeah, and it's pretty hard to eliminate this first binary search. So we kind of need to make at least one binary search in this algorithm. And binary search will take log n time, so this depth is hard to eliminate this log n from here. Okay, next thing. Let's talk about binary search trees. Let's talk about binary search trees. Why? No. Merge sort is done as n log n. It's just linear time complexity for the merge operation. But in merge sort, you need to make merge in each layer, and you have log n layers. Yeah. So total time will still be n log n. Binary search trees. So let's try to do something parallel in binary search trees. Let's do the following. Let's solve this problem. We have a binary search tree. Let's have of size n. And you have some array of n elements. And they're already sorted. So you have sorted array of n elements. So you have n elements in your binary search tree plus n elements in this sorted array. And what you want to do is you want to add all these elements into your binary search tree. So you have some sorted array of n elements, and you want to add all these elements to your binary search tree. So how can you do it? If you just do it sequentially, you just take each element, put it in the binary search tree. It will take log n time, so total time complexity will be n log n, obviously, right? So in one port, so you can add all elements into binary search tree in n log n time. Now, so I want to algorithm work time n log n. N log n. How to do it faster? First, we need some good binary search tree. Not all binary search trees are good enough. So let's use a tree which is called 2-3-3. It's impossible to say. So it's pretty simple binary search tree. It's basically like a B tree, but with B equals to 2. So each element of each node of this binary search tree, it's not actually binary, so has 2 or 3 children. Something like that. So sometimes you have 2 children, sometimes you have 3 children. Something like that. And there's very simple properties that all the leaves of the tree are on the same layer. So the distance from the root to all the leaves of this tree is the same. It's easy to prove that if this is satisfied, then the height of the tree is log n. Yeah. So again, what is a 2-3 tree? You have a tree, you have a binary search tree, but for each element you may have 2 or 3 children. Okay, like if you have 2 children, you have only a single key. If you have 3 children, you actually need to have 2 keys in this. So if you have 3 children, you have 2 keys in this node. Like, you have node like this. So here are elements less than x, the element greater than x. And you have elements like x1 and x2. So here elements less than x1, here are elements greater than x1 and less than x2, and here are elements greater than x2. Yep. Did we discuss B trees? I don't remember actually. So if you know how B trees works, it's actually B tree but with small size. And this tree is balanced because all the leaves of this tree are on the same layer. So if all leaves are on the same layer and you have n leaves here, then total of number of layers can be more than log n. Yeah. So here is n, this is log n. And then last. Yes, we talk about how to build how to build this balanced search tree. Yes, if you just have an array. Yeah, I believe this actually. If you have the same size of the array and tree, is actually quite easy. But yeah, it's a little more complicated when you have m elements. Well, okay, again, if you just have an array, you can build the binary search tree from array in linear time. Obviously, it's not hard. But the problem is you already have some binary search tree. So you want not only build the new binary search tree, you want kind of to add all the elements of your array to the binary search tree, to your already existing binary search tree. You have some pre-existing binary search tree, and you want to add all elements into this binary search tree. So it's not just building elements. So building a binary search tree from the given array of elements can be done in linear time. That's true. Yeah. So how you usually add elements into two tree? You just imagine you need to add one new element to your binary search tree. So you add new element. This new element will be a new leaf. So you just add a new leaf here. Yep. Now, if your parent now has 2 or 3, so it must be 2 or 3. Yeah. So if your parent before had 2 children, now it has 3 children. Now it's a correct binary search tree again. What happens if you add new element and now your parent has 4 children? So if you have 4 children, that's not good. You may have 2 or 3 children. Yeah. So if your parent now has 4 children, we will just split these parents into two nodes. So we take this node and make 2 nodes instead, 1 and 2. And give them both to our parent. Now this element has 4 children. So again, we take element with 4 children and replace it with 2 elements. And we do it until we reach the root of the tree. So again, you add new element to the bottom layer. Now, while you have an element with 4 children, you just split this element into 2. Give 2 children to one element, 2 children to another element. No, invariant is very simple. Invariant is all elements has 2 or 3 children except one. One element may have up to 4 children. And you kind of promote this problem to the top layer. So if you have the problem on some layer, you split the element. Now your parent may have 4 children, so you kind of move your problem up to the tree. And so on until you reach the root of the tree. So if root has 4 children, you just split the root to create a new root. So that's how you increase the height of your tree. So that's how you add new elements to the tree. Now, what happens when you have many elements? Let's move it back. Можно не сейчас. Sorry. Now, what happens if we want to add many elements? So now I have many elements in sorted array, and I want to add all these elements to my array. Well, first of all, let's think about what happens if what may be the problem? What may be the problem? Why can I just add all these elements to array and then fix all the problems? The problem is that all these elements may try to go to the same point of this tree. So if my array is sorted, but all elements are close to each other. So it may happen that all my elements will be put in the same point here. So here I will have many new elements. So this element will be far from normal state. Yeah. So before it has just two children, but if we add all these elements as children to these elements, the how it's called, total degree of this element will be too large. So if I have 10 elements here, I cannot just deal with it. So let's solve the following problem first. What if my elements are such that there's no situation like this? So if I take any two elements here, x and y, then I have some element z from my tree, such that, let's say, x is less than z and less than y. So for any two elements of my array, there is an element of the tree which is between these two elements. What if this property is satisfied? What can we do? No, we can actually add all elements to the tree at the same time. What will happen? So you have some node of your tree. It has, let's say, 3 children. If for any two elements there is an element between them, then we will add at most 3 new elements to the tree. Yeah. Actually 4, but okay, let's deal with the first element separately. This is slightly different when we have the leftmost element, but let's say we have element minus infinity in our tree always. So I can't put elements before my first element. So again, if for each pair of elements in my array there is an element of the tree, then when I add these elements to my tree, I will increase the degree of each node at most twice. So this degree had 3 children. I cannot add more than 3 new children to this element. Again, I add element to the closest element to the left. I find the element, maximal element less than x. So again, you add element x. I find element maximal less than x. Yeah, and add this element right after this element. So I find kind of the lower bound of how it's called. No, it's not lower. No, that doesn't matter. So I find the greatest element before x and add my x to the same parent. If I do it like this, I will increase number of elements of each node at most twice. I can't add 2 elements here, yeah? Because between these 2 elements must be an element from my tree. Now, the degree of each node is at most 6. Yeah, so it was at most 3. I added at most 3 new elements, so now the degree is at most 6. What can you do with element of who has 6 children? Oh, like before, you can split it into 2 elements of degree 3. Yeah. So again, you add all these elements in parallel to my tree. There are some new elements. So we have some new elements here, some new elements here, some new elements here, and so on. Many new elements. Now, in this layer, for each node has at most 6 children. So what you can do, you can split the node into, if node has more than 3 children, you split node into 2. You can always do it. You can always split the node into 2 nodes of degree at most 3. So here degree is 5. You just split your node into 2. So first has degree 2, second has degree 3. Now here we have node of degree 4. So you split it into 2 nodes, first of degree 2 and second of degree 2. And so on. And so on. Here you have degree 5, again you split it 2 and 3. Now you go to the next layer. In the next layer again, you so have the same. Now, here everything is cool, yeah. But here we have some bad nodes which has degree more than 3. You apply the same thing. Again, you can do it in parallel. You can do it in parallel for all nodes in the same layer. So again, first we add all the new nodes in the bottom layer. We can do it in parallel. It's all independent. Now we go to the next layer and fix everything in this layer. So we find all the nodes which has degree more than 3 and split them into 2 nodes. Now we go to the next layer and fix everything here. So here we have 2 nodes. They have degree 4. So we split them into 2 nodes. And this. Now, here everything is cool, here everything is cool, here everything is cool. Now we go to the top layer, and here we have the root. Root has degree 4, so we split the root. And finally we have valid 3. Okay, this picture is kind of messy, but I hope you got the point. Yeah. So if this property is satisfied, then we can easily add all the elements at the same time. So again, we take all the elements of the array, add them in the bottom layer in parallel. Now we go from layer to layer and try to fix all the nodes of degree more than 3. So we take all the nodes of degree more than 3 and split them into 2 nodes. Then go to the next layer, fix everything here. Go to the next layer, fix everything here. We have at most log n layers. So the depth of this algorithm will be log n. So let's put something here. Let's put it here. So work is n log n and depth is log n. But now, that's only true if I have this property. So if for each 2 elements, I have elements in the tree between them. What if not? What if not? So let's say you have some random array of sorted elements. What can we do? First, let's add the middle element to array. So let's take this middle element and add this single element to my binary search tree. We can do it, yes? We can add 1 element. Now, we can add 2 elements. We can add this element and this element. Because we know that for these 2 elements, there is an element which is already in the tree and which is between them. Yeah? So we first add this element. Now we can add these 2 elements. Because they know that for these 2 elements, we have the element which is already in the tree between them. Which? When split nodes more than 3 children, not we create balanced node. No, why can we do balanced? Tree is balanced because all the leaves are on the same layer. We always add leaves on the same layer, so the length, the height of the tree can't be more than log n. No, the degree of each node is at least 2, so degree is 2 or 3. So degree of each node is at least 2, and all the leaves are on the same layer. So here we have n nodes, here we have at most n over 2, here we have at most n over 4, and so on. So the depth will be, the height of the tree will be log n. Now, so I added this element first, then I can add these 2 elements, then I can add these 4 elements, then I can add these 8 elements, and so on. So in log n steps, I will add all elements to my binary search tree. So again, I kind of do it in waves. So in first wave, I add this 1 element. After I add this element, I can add these 2 elements because this element is between them. After this, I can add these 4 elements because for each pair of elements, there is elements which is already in the tree. And so on. So I add this element, then this element, and so on. In log n steps, I will add all my elements to the binary search tree. Now, If you do it like this, then you have log n steps. Let's say log m, just sorry, m elements. So length of array is m, just to have two different constants, right? So if I have array of length m, I have log m steps here. For each step, I make all this thing. This thing has a complexity m log n. And depth will be log n multiplied by log n. Like this. That's all. That's all. Can we do better? We actually can. We can improve this depth slightly. We can do it. I think it's called pipelining or something. It doesn't matter. So what we can do? We can kind of cascade all these changes. So first we add the first single element. We add this element, and then we fix the binary search tree from bottom to top. When we fixed two bottom layers, we can start adding these two elements. So we add the first element, then go up and try to fix everything. And while we're going up, we can add these two elements and try to fix everything. So we kind of have these waves. So we add the first element and go up, fixing everything. And when we reach this like first layer, so this first wave, we add two new elements here, these two elements. And again, go up, try to fix everything. And we have a new wave of fixing, and so on. So in each step, we can actually parallelize these steps. So we make first step, then fix everything, then take second step, fix everything, and so on. So we have these waves, and they're going up simultaneously. If we do it like this, the depth will be like log n plus log n. It's slightly harder to implement, but again, time complexity will be slightly better. Okay, I think it's enough today. Okay, so thank you for coming. It was nice to have this course for these 2 years. I hope I see you again sometime. Whew. Anything else? I think so. Yes, thank you. Bye.